Hello everyone. Welcome to all of you to in the new tutorial video. I am Mr.Rimon with you from United International University, Bangladesh. So today it's basically our tutorial video or lecture number 6. So in the previous tutorial video, we was discussed that how to plot .dat files in LaTeX. So we're using some .dat files. So those .dat files were generated from Cadence, where the axes represented the gate to source voltage or VGS of N. So N means NMOS. We're using NMOS, and the y-axis, those are represents the parameters. So if you recall that, the parameters such as like VDSAT, FT, into GM over ID, and then we have GM over GDS, we have GM over ID, and then we have ID divided by W. So there are tons of parameters that actually you have. It depends on your design, which parameter is actually you need. So whenever we plot, we can see that the plot is generated with respect to the x-axis as a VGS of N, and y-axis this may be any parameters. Individually, we actually plot these in LaTeX. So actually, the Cadence generate the plots against VGS. Why? Because we are using the DC sweep, and our sweep variable is actually VGS of N. If you recall that, our sweep variable was VGS of N. So Cadence basically by default plot all the parameters against VGS of N. Parameter versus VGS of N. So we extract the DAT files. That DAT files also contain this parameter versus VGS of N's value. However, GM over ID based design, the plot with VGS on x-axis are not sufficient. So if you consider the GM over ID design, in the case your x-axis will be VGS of N, it actually not sufficient. And this type of curve, that means parameter versus VGS of N, this type of plot actually not enough for analog circuit design. Instead, we require plots where basically just GM over ID in x-axis. All right. and all the different parameters are shown on the y-axis. So the last tutorial, that means tutorial number 5, this class is actually uh, mainly served the introductory section on LaTeX. So that was the introductory section on LaTeX. I try to demonstrating, that is, how to .dat files can be plotted using basically LaTeX. All right. So although Cadence does not directly provide you the plots with such as, like, for example, GM over ID in x-axis and your parameter in y-axis. So Cadence basically does not directly provide you this type of plots. If you need for circuit design purpose, some plots where at the x-axis is basically your GM over ID. All right. So in this case, you need to generating such actual model simulator plots. It is not difficult and requires only a small additional effort. So we can plot the parameter versus GM over ID in Cadence. This is possible, not impossible. I will demonstrate how to plot parameter versus GM over ID in Cadence in a future separated tutorial video on it in details. So today, basically what we will see, that means what is the outline of this tutorial class. So after the end of the segment, the student should be able to explain more things from today's class. So if you see here, your number 1 outline is how to extract .dat files from Cadence. Okay, where the x-axis will be your GM over ID, and the y-axis will be show different parameters. Okay, so this is the first outline. Second of all, we actually try to understand the .dat files. Try to understand the .dat files. That means we need to analyze the data structure, and do some modification on the data, and prepare them for plotting in LaTeX. for plotting in LaTeX. After that, we will setting up the dot files for LaTeX for plots in the correct format, and then we will show a brief demonstration of plotting the extracted .dat files using the overleaf. And finally, we plot in LaTeX and generate curves, which is actually parameter versus GM over ID. Any parameter, for example, we choose for today's class GM over GDS versus GM over ID, and then we are considering for for example, ID divided by W versus GM over ID. Okay, and do the same thing in Cadence. That is, we try to generate these two curves also in Cadence, and after that try to see the similarity of Cadence plot and LaTeX plot. So basically, in this class we try to cover this content, and this is the outline of today's class. So after the end of the segment, the student should be able to perform those things. So before I start the class, I want to show some plots. So let us discuss about them. So the last class, we are plotting some .dat files in LaTeX, which I mentioned here at the starting of the tutorial video, in the today's video. So the .dat file we are extracted from Cadence, and those .dat files corresponding value that I get that was parameter against VGS of n. For example, you consider the overdrive voltage versus VGS of n .dat files, and then you have all the .dat files up to, for example, ID divided by W versus VGS of n .dat files. So basically, we are generating 7 .dat files from Cadence, which plot are actually containing the y-axis parameter and x-axis as a VGS of n. So that are actually we covered in the last class. So I try to show those plot at first, and after that we will start today's class. So let me just open the overlay. So the project was saved by using tutorial 5. So if you see here, inside this project, I am creating two folder and some files. So if you see here, we already discussed some that I have to plot in the last video, and I have completed all the plotting of the .dat files. So let's see them respectively. So if you see the first one, This is ft into gm over id versus vgs of n. So if we compile that, so we can see this plot. So let us see presentation mode. So you can see that this is basically our ft into gm over id curve, which I am actually plotting in overlay for LaTeX. After that, I plot the ft versus vgs. So now let us see the curve. So I'm using here the legend. So go to the presentation mode, and you can see this is the ft means unity gain bandwidth. All right, and your x-axis is actually gate to source voltage, that is the VGS of n. And I am here different color of length, and the corresponding length are mentioned by using this legend. So then we see the GM over GDS versus VGS of n. So you see here, basically see here, this is your intrinsic gain versus your gate voltage. So you get this type of curve. So based on the parametric analysis, we are starting from our parametric analysis, our minimum value that was mentioned here, which is 100 nanometer, and the maximum value, which is 1.9 micro. So the incremental step size that I'm using here, that is 2. So it will increasing the length, or the dat file is generating the length for like 100 nanometer, then 300 nanometer, then 500 nanometer, then 700 nanometer, like that. So it will increment with 200 nanometer at a time. And by studying of our .dat file, we actually set our x-axis range. For the VGS of n, the range is from, that limit is actually from 0 to 1. We study the .dat files and get this value. And similarly, we study the .dat files and get the suitable range for the y-axis. That means I want to say that the range is in between in this value. This is actually explained by using the .dat files that I have. So if you see here, we have GM over GDS .dat files. So if you study these .dat files, inside all the data are given. You can find out your y-axis maximum and minimum value, and x-axis corresponding maximum and minimum value. And you need to actually specify this value in your program. Otherwise, it may not be work. So here, and after that, we plot the GM over ID versus VGS. So let us see. So this is your GM over ID versus VGS. So this type of curve you have. So I am using here also legend. If you are not interested for legend, you can skip it. Okay. So this is actually your GM over ID versus VGS curve. And after that, we have ID versus W, ID by W versus GM over ID. So you see here how nice the curve. how beautiful the curve seems like. But in Cadence, you cannot actually plot this type of fresh, clear, and good looking curve. So that's why we are using the alternative method to plot our important .dat files. So after that, I plot the VDSAT versus VGS of n. So if you see here, so this is your VDSAT versus VGS of n curve. If you change your VDSAT, the corresponding, you have suppose a VGS of n. For the typical value, the point will be may intersect any of this line. For example, here. For example, suppose here. Then you what will do? You will do the interpretation. All right, which is the accurate length you need to make measure from here. So that is a very crucial adjustment. Okay. So finally, we have the overdrive voltage versus gate voltage, gate to source voltage. So if I compile it, you can see this is the overdrive voltage versus gate to source voltage curve. So it will look like this. Okay. All right. So that is the demonstration that I am actually want to show, because this is the part of the last class. Okay. So now it's time to start our today's class. So let us go to the presentation slide again. So so the outline of today's class, I want to discuss these things again. That is how to extract the .dat files from Cadence, where is the x-axis will be GM over IT, and the y-axis will be so different parameters. And second of all, we try to understand the .dat files. That means we try to understand the data structure, then modification, and after that prepare them for plotting in LaTeX. Finally, we plot our curve in LaTeX. For example, we are doing today these two parameters, let's say GM over GDS versus GM over ID, and ID over W versus GM over ID. And then similarly, we plot these two parameters in Cadence, and after that, we try to interpret those things. How similar they are actually, and what is the difference in between them. So let us start today's class. So if we want to start today's class, at first we need to open our Cadence. So we need to log in our Virtuoso. So this is our directory where we actually performing our GM over ID analysis. So let us the terminal open in here. And right here CHs, and then right here Virtuoso, and then launch it. So we need to open our file. So our library name is GM over ID. And inside the library, I have my cells. So I want to open the NMOS OPT. So basically, this is my schematic window. Now go to the launch and ADEL. After that, load state the saved analysis that I'm doing before. So this is the load state. So click OK. Then everything is there. So now let us run the simulation. So we will enable shape, enable plot, and then run it. Okay. So the simulation is actually successfully done. There is no error here. Okay. So now we will minimize those things. And let us unplot them. Enable plot. Sorry, disable plot. Okay. So we need to generate a parameter versus GM over ID dot files. Dot files. So these are my parameter. So these all parameter are contained in y-axis, and x-axis should be GM over ID. So for this region, we need to do analysis for different length. So for this region, we are using here one more extra analysis, that is the parametric analysis. So in the parametric analysis, we basically sweep our channel length. So here we have 5 variable. We are interested to vary the length of NMOS. So click here, and we want to suppose try to vary from the minimum is 100 nano and maximum, say for example 3 micro. Okay, and then our step mode linear step, and total steps will be for example 200 nano. So if everything will be okay, the simulation will be run successfully. But we try to plot, say for example GM over GDS with respect to different length. Try to see whether the plot is actually work or not. The simulation is actually executed, and it will generate some curves where y-axis is GM over GDS and y-axis will be G VGS of N. So now you can see that this curve for different length. So if you see here, this is for 100 nano, this is for 300 nano, this is for 500 nano, this is for 700 nano, this is for 900 nano, and up to 2.9 micro, because we are using here 200 nano step size. Okay. So now let's close it. So basically we need to save all the datas in Cadence by using the parametric analysis. So we will do these things again. And after that, we will save the parametric analysis. So let us minimize this. So go to here. You have save option. Find your directory. So we go to the work, and then we have here GMO ID. So let us save it here. Say for example in this name NM0 param final, and then save it and click it yes. So after that, the analysis will be saved in that folder, and now we will do a little bit ocean scripting. So go to the file and click on the save ocean script. So for this region we need to rename here in name. So let's say for example NM0. Why NM0? Because our NMOS is uh, NM0 here. So you see here this is NM0. It need not to be necessarily mention the same name. It will not occur any error. But for the similarity maintain, I write here NM0. If you want, you can use any other name, no problem. So NM0 then underscore parametric analysis of param, and then final, then game over ID, and then save the ocean script. So now we actually close this one and try to open the file. So go to our terminal and write here gedit, then nm0 underscore param. P will be capital letter param underscore and underscore gm over id dot ocn. So if I write this in gedit, we can get our parametric analysis data. This data are we extract here. This is the sweep length parameter 100 nanometer to 2.9. All right. So for this region, we need to do here a little bit ocean scripting. I have already written the ocean scripting earlier, so I will directly use it here. So this ocean print function will generate our .dat file. So if I explain a little bit here, we are interested to see output, and then we actually define our exact directory and location. And after that, we actually write here the dat file names. So these dat files is actually VOV versus GM over ID. I write it here. But in the scientific, after that you use a GM over ID, so it means that it is actually in x-axis and VOV in at y-axis. So try to make sure the similar variable you actually write here. Unless you do that, the ocean script will not execute properly. So that will be a very big problem. And then you have basically And then you have basically GM over ID. So we need a plot that is GM over ID versus overdrive voltage. So this type of one plot we need. So let us copy it and then paste it and write the name that is VOV versus GM over ID versus GM over ID versus VOV .dat files. So in that case, your x-axis will be VOV and your y-axis will be GM over ID. So after that, you have overdrive voltage, that is VOV. So this is your VOV. If you see here, this is actually it will be like it will basically like VOV versus VOV versus GM over ID. VOV versus GM over ID. So let me just do a little bit renaming here. Okay, 50 versus GM over ID. All right. So I think everything is done. So now we will actually save it, and after that we will execute our ocean file. So carefully check all the things, and after that save it. And whenever it will save, you just minimize this window and find out your ocean file and go to rename and copy all the name of your ocean file. Then come back to the location and give it a backslash n and paste your ocean file. And after that, you will copy the whole things. Okay, so this is the procedure. And after that, what actually you do? So now I actually execute the ocean file and generating the .dat files where the x-axis will be GM over ID and y-axis will be different parameter. So let's click on the virtuoso and this is your cds.log file. So we need to use here a function that called load and then use a double quotation and just paste our ocean file with exact location. Unless you mention the location of your ocean file, the load function cannot be execute your ocean file. So very carefully you need to mention the exact ocean file location. And after that, you close the double quotation and then press the enter. So this is actually starting the execution of your ocean file. So it takes some time. You need to be patient at this moment and try to observe your cds.log window there is any error is actually occur or not. If there is any some error, it will be uh, creating a problematic situation. Then you actually fixing your error, and after that you again simulate erosion files. So that's a problem. But in my case, uh, everything is successfully done here, so there is no error. Now, what will actually I am do? So basically, I will uh, creating a new folder to extract the .dat files. So let us create a folder and give the folder name is, let's say, nm0 uh, final dat files. Final dat files. So this is the name of the folder. Now I actually copy the .dat files. So this is the first one. So you see here, this is ft gm over id versus gm over id .dat files. This is ft versus gm over id .dat files. This is gm over dds versus gm over id. This is gm over id versus overdrive voltage. This is id by w versus gm over id. And then try to finding the next one. So this is basically VDSAT versus GM over ID.dat files. And this is your gate to source voltage versus VDSAT, GM over ID. And finally, this is your overdrive voltage versus GM over ID. So I think these are my .dat files. Now I just simply card those dot files and then paste those in this directory. So these are my .dat files, very important .dat files, which .dat files we will plot in LaTeX. So if I open a .dat file, you can see that there are tons of data. You cannot actually understand what is actually this row and columns are implies. It is basically very difficult to understand here. So we need to apply here some modification, and for this region we will just simply copy this folder and then we will go back the Windows, and after that just paste that folder. So that's it. So you can see here inside this folder you have all your .dat files. So now if you see the outline of today's class, so this outline is actually how to extract the .dat files from Cadence, where x-axis will be GM over ID and the y-axis will be 4 different parameters. So the video length is actually pretty much very longer, and I want to do the part 2 of this tutorial 6. So we need to be written here something like, say for example, just a little bit. We need to editing here. So today, basically, we covered successfully this one outline, but the remaining outline we didn't touch yet. But the video length is very longer, so that's why I want to stop the video right now and try to make the part 2 of tutorial 6. Okay, so these contents, that means this one, and this one, these three content I will cover the next video, that is in tutorial 6 part 2. And this is the ending of the tutorial 6 part 1. Tutorial 6 part 1. So the next tutorial video, I will explain these remaining outlines in details. So we can end here. That's all for today. And with this, I conclude this tutorial. Thanks for watching and subscribe my channel.